in high energy physics. So
Okay.
the stage is yours.
Yeah, so it's a pleasure to be here, especially because I studied here. So in this lecture hall, I learned all my electrodynamics and quantum mechanics and so on. So it's great to be back, and thanks for the invitation. So I was invited to talk a little bit about machine learning applications in a related field, so not lattice QCD, but high energy physics. And so I wanted to give a kind of broad overview of kind of the way that we are thinking about things. And so the way that I often kind of start these talks is to kind of build up a little bit of tension on what's been happening in the last 10 years. And so you might remember, so 2012 was a pretty big year in particle physics, but also turns out a pretty big year in machine learning. And so there are two things that happened. So as a physicist, you might know that, okay, the Higgs was discovered. And so that was kind of one of the main scientific highlights probably in physics in the last decade. But at the same time, there was also a graduate student in Canada that was looking at deep neural networks. And for the first time, they developed a kind of computer vision system based on purely end-to-end trained deep neural networks that kind of is now named the AlexNet moment. And so this really kickstarted this deep learning revolution in the last 10 years. And so you see both of these New York Times articles. There's also one article that has funding frenzy escalates, and so, but it's the deep learning one, not the particle physics one, unfortunately. Okay, so these two things happened 10 years ago, and they tell us different stories of what works. And so this is an example of Higgs decay that we recorded in the data. And so we can kind of think of how we managed to discover the Higgs. And so here it kind of looks hopeless. It's a lot of data. It looks very complicated. And so the Higgs discovery is really kind of like a triumph of domain knowledge, right? So you have this gigantic detector. You have 100 million channels that we have 40 million times a second. We record data. We have an order of petabytes of data every year. And so from this, we infer physics at the smallest length scales, right? And so that this works is astonishing, right? And so how do we do it? So we need to bridge this very big gap, both in kind of dimensionality. So the theory is simple, has order 10 parameters, and then the data is order 100 million data channels, and so there's a gigantic bridge between these two things in data dimensionality. There's also a gigantic bridge between energies, so the energy scale at which we define the theory is very different than the energy scale at which we actually record the voltages and so on. And so we need to somehow bridge this thing, and what we want to do is that we want to learn kind of, okay, what does the data tell us about the fundamental parameters of nature? Okay, so how do we do it? One of the main kind of saving graces that we have is that we know the physics very, very well. So we can bridge this gap in energy scales by applying like a sequence of physics theories to this. So we start with quantum field theory to compute matrix elements and so on. And then we have effective theories for QCD to describe the evolution of this hadronic collision. And then we know nuclear physics very well and how material, like particles interact with material to simulate the detector response. So we can walk down this energy scale by applying the appropriate physics theories one by one. And if you write it down in a statistical way, it looks a little bit like this Markovian process of starting out with a theory and then you walk down with these conditional distribution. And what each of these things is a theory. Okay, so that's great, and so this helps us a lot. The problem is that, okay, in order to actually think about, okay, what is the likelihood of a single event given some physics parameters, you would have to integrate over all the possible paths, kind of like a path integral, how you could walk down from the theory to the data that you have. And so you would need, so there's lots of kind of intermediate states that we don't actually observe. We don't actually observe the partons. We don't actually observe the details of the parton shower. And the only thing that we actually observe is the voltages at the very end. So we need to integrate over all the intermediate states. And so this is a million-dimensional or a billion-dimensional integral. And so this is completely intractable. And so this is why particle physics is called to be likelihood-free. Okay, which is not a good thing because, okay, if you wanted to do this with standard statistics, you need to have the likelihood, but we don't have it. Okay, great. So then, what do we do? So a standard kind of statistical inference doesn't work, but we can kind of approximate statistical inference by using our physics knowledge and our knowledge of all these effective theories and putting them into computer code, and then we write simulators. And so at least while we cannot evaluate this likelihood, we can sample from this likelihood stochastically, and we can generate for any type of theory that we want, whether or not it's a standard model or beyond standard model physics like supersymmetry. We can generate Monte Carlo simulations of what this would look like in our detector, and with these simulations we can then do our science. And so by turning our physics knowledge into software, we actually jump over this obstacle of not having the likelihood. And so we have a lot of different simulation codes like event generators, Parton shower simulation, detector simulation like JON4, and so on. Okay, so how good are these simulators? These simulators are extremely good. So here you see an example of a comparison of the data that we have at the LHC with, compared to simulation. And so you can see this is spanning 8 orders of magnitude, and the data and simulation agree extremely well. So particle physics is one of the few fields where the simulation is very, very trustable and very good. So we know there are limits to it, but to first order, we trust the simulation to a very high degree, and it's kind of like the backbone of how we do science by comparing the data to the simulation. Okay, so then, we still have this thing that we can simulate things in a 100 million dimensional space, but it's impossible to do like a density estimation in 100 million dimensions, right? So you can't, fill a histogram of all the possible realizations of, what the detector and the detector data looks like, and so you need to find projection or compression of all of this, diluted data. So, the Higgs information is somehow diluted in these 100 million channels, and we need to collect it back together, hopefully without a lot of loss of information. So what we try to do is we try to go the inverse direction than what we had kind of here. So this is the simulation direction, which is going from the theory to the high-dimensional data. And here we want to go in the reverse direction. This is what we call reconstruction and analysis. And so here we want to go from the high-dimensional data into the language of the theory again. And so we do this by a hierarchical reconstruction. So we do a lot of, for example, particle tracking, calorimeter clustering, particle identification, event-level observables, and then finally we do statistics. And so this is the reverse direction. And what is interesting here is that we don't know what the best way to represent the data is, right, a priori. We have no idea what the best way is to compress the data from these 100 million dimensional space to a low dimensional space, like a one-dimensional distribution, and we need to find this optimum. So it's an optimization problem, and this is where machine learning comes in. Okay, while we cannot get the true posterior, we can maybe get the posterior on some representation, low-dimensional representation of the data, but we want to do this without losing a lot of information, and so this is becoming an optimization problem where machine learning is expected to help a lot. All right, so how do we do this? So the way that we do this is kind of in a hierarchical way. So Julian already mentioned hierarchical setups, and so this is kind of the bread and butter of particle physics. And so we basically, split this high-level problem of coming up with a one-dimensional distribution or one-dimensional summary of a 100 million dimensional object by splitting this into multiple subproblems. And so all the reconstruction steps that we have are basically about clustering things together and then representing them. So we want to group together hits in the particle tracker to combine them to tracks, and then we want to find track parameters. We want to group together energy cells into energy clusters, and then we want to somehow represent the energy cluster with the properties. What is the distribution of the energy in the cluster? Then we want to kind of combine tracks and clusters into particles to combine, for example, like a calorimeter cluster with a track to form an electron, and then to invert the potential, we do things like jet clustering, and then finally we do, we reconstruct resonances like this. Okay, so it's always kind of the same idea. We group things together, then we represent them. And the question is, okay, what are the right grouping operations that we have to do, and what is the right way to represent this new grouped object? And so this is, where machine learning plays a big role. Okay, so then, so the main story of the Higgs discovery, so you might have seen this thing, which is basically tells you the invariant mass, the reconstructed invariant mass of 4 leptons. And so you see very nicely the Higgs peak. And so this is basically the perfect example of this compression from 100 million dimensions to a single dimension. This worked very well. You can see the Higgs already kind of by eye. And the main message of the Higgs discovery is that kind of domain knowledge works, right? So we use all of our physics knowledge to kind of solve this problem. And if we do it correctly, good things happen. Okay, so that's the first thing that happened in 2012. Okay, so then the second thing that happened, you might have seen things like this. So image generating AIs, where you can go from a very abstract kind of representation of an idea in terms of natural language to something like this, right? And so this is, one of these image generating AI, like stable diffusion and so on. And so what is happening here? And so deep learning, unlike particle physics, is not a triumph of domain knowledge. It's a triumph of data and scale, right? So these image generating AIs were trained on kind of petabyte scale training data. And so they are able to, from this natural language sentence, generate 3 million floating point values, from scratch, right? And so it's very important to note that, okay, if you put this sentence into the image generating AI, it's not trying to first generate the head, and it's generating the face, and it's generating the hands, and so on. It's just kind of outputs directly the pixel values, right? Okay, so how did the machine learning people do it? And so they didn't implement any type of, a priori knowledge about what faces look like, but they just have internet scale data, not least because the CERN invented the World Wide Web. And then we have massively parallel computation, where kind of in the early 2000s, people understood that they can do, parallel computation or general purpose computation on GPUs. And then, you have kind of trillion-dimensional optimization problems and an efficient way to navigate these very super high-dimensional spaces in terms of gradient descent and finding locally a good optimization path. Right? And so these are kind of the 3 main ingredients to machine learning. And so you'll notice that there's not a lot of domain knowledge about what a face looks like in these things. Okay, so then what is happening? So, okay, it's kind of the same thing. So the what we call reconstruction, so going from raw pixel data or like raw detector data to like a high-level concept representation. This is what, for example, convolutional neural networks do. And so they also learn to hierarchically reconstruct something, but instead of using kind of interpretable things or, like the human puts in what to reconstruct, the machine learns itself, right? And so early on, you can see that it's learning things like edge detection or curve detection or, texture detection. But it's not as interpretable as what humans do, and the machine kind of learns this on its own. And then the reverse direction is now also possible, which is what image generation is. You go from this high-level concept like natural language, and then you go to the raw pixel data, and you don't do it in a hierarchical way like we do in terms of describing the physical process of what it means to generate a picture like this in terms of, for example, ray tracing and rendering and so on. It's not how these images are generated, but they're basically just transformed from raw noise, and through fairly uninterpretable transformations like this image appears of, like an astronaut riding a horse. Okay. So, this is all summarized by Rich Sutton, which, in a very famous essay called The Bitter Lesson. So he is one of the pioneers of machine learning and especially reinforcement learning. And he's been saying that, we as researchers, we seek to leverage the human knowledge, but the only thing that matters in the long run is the leveraging of computation, right? And so it's kind of, for a physicist, a little bit, I mean, not only kind of like a depressing message that, we want to induce our physics intuition into these machine learning systems, but the story of the last 10 years has been, it's less important, and it's more important to have high quality, large scale data sets and very, very big models. And so these two things are a little bit in tension. Okay, but they're in tension, but in the end, they solve the same problem, as you will notice. And so in the machine learning, or in particle physics, we go from a high-level concept, which is like the Lagrangian formulation of physics, to the low-level data, which is the 100 million kind of raw sensors that we have at the LHC. And so this is the simulation pipeline. And then here, what we call reconstruction is basically going from the raw pixel data back to this high-level language of physics. What machine learning does is basically the same thing. So the image generative modeling side is basically going from a high-level concept, which might be natural language, to the raw pixel data. And then you can also go in the other direction, where you might have things like image captioning models that take the raw pixel data and give you a sentence of what they see in the image, right? And so it's exactly the same type of dynamic of what is happening in particle physics. And so then you can ask yourself, okay, it's very impressive what has happened in the last 10 years in machine learning, and it's nice to see, but should you care? And so in particle physics, I think the answer is yes, because of the similarity of what we're doing, so both simulating and also pattern recognition in the other direction. All of these developments are extremely relevant for particle physics, and it's not by chance that the first application of neural networks in particle physics has been in the late 80s. We can argue that, okay, the future gains at the LHC will primarily come from improved methods, and so that we can solve this optimization problem and get as close as possible to the true posterior by having a clever compression of the data, which might be learned by machine learning systems. All right, so how can we use machine learning in particle physics? And I see there are two main directions. So there are situations where you don't know the right answer, and this is kind of the reconstruction side. We don't know what the best way is to represent the high-dimensional data, and we want to optimize this. And so we want to search for the best algorithm, the best tracking algorithm, the best jet clustering algorithm, the best analysis observable. And so when you don't know what the right solution is, a good way is to search and optimize in like a possible space of solutions, right? And so this is kind of the classic situation for machine learning. But then there's the other direction, which is, okay, sometimes you know what the right solution is, but the right solution is slow. And that's, for example, in simulation, where, okay, we don't think that the machine learning system will learn like a better model of how to simulate physics, because we understand the physical theories very well, but it might help us do this faster, and especially in an era where kind of the computing landscape is changing rapidly, and a lot of the kind of core technologies to convert transistors into something useful as in computing devices is shifting more and more towards AI and special purpose computing devices instead of general purpose computing devices. Translating your simulation problem into a machine learning problem might also be very, very helpful. Okay, so now we can ask, okay, how do we solve this tension? What is the lesson of these two stories? So does this, do we kind of agree that domain knowledge is obsolete? And so I think the answer is very nicely represented by these pictures. So this is also what you see from these image generating AIs, right? So you can say, okay, give me salmon in a river, it will generate something like this, or we'll say, okay, what is this? Reconstruct, okay, what's in this image? It will tell you an iPod. Okay, this is a very dated image because iPods don't exist anymore. It's clearly at the level of precision that we want to do in particle physics, or maybe also lattice QCD. You want to have strong guarantees of correctness. And so domain knowledge I think we're not at the level yet where we throw away everything and we leave everything to the machines. All right, so then what this means in machine learning lingo is we want to bias kind of the search space of possible solutions to the ones that make physics sense. And so this is sometimes called inductive bias. And so instead of having kind of like a black box machine learning system that just maps from inputs to outputs, you want to have something where you're kind of adding some physics computation. And so there are two ways to add kind of physics sense to a machine learning system. So you can enforce something into the machine learning model itself. And so, for example, things like symmetry, so energy conservation or Lorentz symmetry and so on, you can try to find neural network architectures that naturally represent these symmetries. And the other one is to kind of mix and match machine learning models to not replace everything with one gigantic neural network, but have like physics-informed computations, and then at places where it makes sense, you add machine learning models. All right, so so this has been going on for quite some time, and so there are lots of symmetries that already the machine learning researchers have found. So things like translation symmetry, so convolutional neural networks kind of represent translational symmetry. But of course, you can't stop a physicist from playing with symmetries, and so a lot of work has been going on finding kind of particle physics specific neural network architectures that have specific symmetry properties or physics properties. And so here just some examples. So there are neural networks with QCD-like structure, gauge equivariant convolutional neural networks, so extending the idea of translation symmetry to gauge groups. Okay, Julian already showed this SUN equivariant normalizing flows. Infrared and collinear safe networks are also kind of an important idea in particle physics, Lorentz invariance, of course. And so there's many examples of trying to have physics-inspired or physics-informed neural network architectures. So then how do we use, or where can we use machine learning? So let's just go through some examples. And so in reconstruction, I think the story in particle physics is basically that machine learning is already everywhere, and so it has been for many years. And but there are basically always very small targeted modules in like a very large hybrid system. So we have like a physics-informed reconstruction pipeline of what we're trying to do, and then at very specific points we leave the job to the machine, and it does its job. And so examples are flavor tagging, so identifying jets from heavy flavors, particle identification, reconstruction from missing energy, vertexing, analysis observables, and so on. And so what's noticeable is that, so right now, there's no role for these very big billion parameter scale models like GPT, what you see in industry, right? And so you can ask yourself, why did this, or where, this would, whether or not this would have a place. So this works very well, it has been working very well, it's very interpretable, but it's not obvious because it's an optimization problem. It's not obvious whether like this level of machine learning is the right level to reach the optimum, or whether or not you want to have more machine learning or less machine learning, right? And so it's not, so whether or not this is the optimal extraction of information from the raw pixel data is not clear. Okay, so then, one of the trends that has been happening over the last couple of years is that you have, a trend towards bigger and bigger components, right? And so we can have like a little bit of a split of responsibility. So the responsibility of the human is basically to impose kind of what are the relevant degrees of freedom. So impose the overall structure of what the computation should look like, and then leave all the details of what the actual computation is going to be to the machine. So for example, if you say, okay, I want to have like a energy conserving observable, you find like a neural network architecture that is energy conserving, but then what the computation itself should be, this is something that you leave to the computer, and you have bigger and bigger models. And so here are a few examples. So particle tracking, there has been a lot of effort to see whether or not you can replace particle tracking with, a very small number of very big neural network components. And tracking is a very, very strong baseline to beat, and so it's not obvious that this will happen, but people are trying this. There's a lot of work on kind of automating the end-to-end identification of particles from the raw data. So this is called particle flow. So once you have the tracks, you combine this with the calorimeter information to get something, get the data into a language that the physicists understand. So they're like the particles and their momenta. And then a lot of work is in kind of finding representations of jets. So jets are sprays of particles kind of as a result of parton showers. And so they're very high dimensional objects, and whether or not our kind of traditional jet representations in terms of like a single four momenta or like a few moments is optimal is not clear. And so you see a lot of work in kind of finding very big models for QCD jets. All right, so there's one idea that kind of gives you both of these ideas where, okay, you might have like this joint model where you have a lot of physics computation and then a few machine learning models. And now the question is, how do you jointly optimize these things? Traditionally, what we do is we optimize each of these blocks independently, but whether or not a sequential optimization is the same thing as a global optimization is not obvious at all, right? So for example, in chess, you instead of optimizing only the next best move, you very often optimize, okay, the next 5 or 6 moves. And so ideally, you want to have like a joint optimization of the end-to-end pipeline. And so the way to get basically the cake and eat it too is to make this pipeline differentiable. So Julian already mentioned this. So the way to train neural network is through gradient descent. And if you want to have like a hybrid system that includes physics computation into like a neural network, other than symmetries, you want to have all the physics computation that is between these machine learning blocks to be differentiable so that you can still do backpropagation and like an end-to-end optimization. And so this allows you, for example, to include systematic uncertainties into your pipeline. And so very often if you only represent something as a machine learning problem, for example, signal versus background optimization, it will try to find a situation where the signal and background, the background is suppressed maximally, and then you retain a lot of signal. But this might be a region where you have a lot of systematic uncertainty, which the machine learning model might not know. And so the physics optimum is actually somewhere else where you accept a little bit more background, but what you gain is like a smaller systematic uncertainty. So the overall sensitivity that you have for your physics output is better for a different setting. And so you can find this different setting only by integrating the systematic uncertainty evaluation into your optimization procedure. All right, so then there's a lot of work on differentiable physics. So not only in particle physics, so there's differentiable matrix elements. So this is a paper we wrote. There's differentiable proton structures. So PDFs are now very often they were trained with genetic algorithms. Now you can also train them with backpropagation. Differentiable parton shower, even differentiable string theory. And so there's an entire cottage industry on trying to find ways to integrate physics computation into machine learning computation. Where is the place for these very big models? And so this is sometimes called foundation models. And so is there something like a foundation model like ChatGPT in store for physics? And in a way, the structure is very similar. We already have a foundation model in particle physics. And so this is our reconstruction. We have like a common step that everybody uses to turn the data into something that physicists understand. And then the grad students, they work on this representation of the data. And this is exactly the same setup that large language models, for example, have to turn raw text into a high-dimensional representation that then can be used for, for example, fine-tuning whether or not the review is positive or negative, right? So you train on all of Wikipedia to have like a general language understanding, and then, okay, for any specific task, you never go back to the raw data. You might use some pre-reconstructed representation. And so this is very, very similar. So what we don't have in particle physics is this idea of kind of self-supervised learning on how you train this backbone. And there's a lot of kind of recent work now to see whether or not you can extend these self-supervised learning techniques to particle physics as well. And so this is one example. Okay, so then I will not spend much time here. So all of the stuff that I talked about, this gets even harder if you want to do it in real time. And so in the trigger, when we have 40 million collisions every second, we need to basically do like a fast version of this. And so a lot of people are looking into how you can embed these more and more complicated machine learning models that are appearing into this real-time environment where you need to put these machine learning models on things like FPGAs. And so on. And so this exploits kind of both aspects. So you want to have a better trigger in terms of like a better trigger algorithm, but you also want to put it on very specific hardware. Okay, so then, so this was the reconstruction side. So how can we use it on the simulation side? And so simulation, as I mentioned, is very, very important in particle physics. It's kind of the backbone of all the physics that we do. And it's a large fraction of also of our computing budget. And so in a way, you can ask yourself, okay, if machine learning can generate photorealistic images of persons and so on, can it also generate realistic representations of particle physics? And so here's an example. So you can kind of go through all the steps in the simulation pipeline and see whether or not you can use machine learning there. And so, the first step is kind of quantum field theory. And so there we basically have the amplitudes that we get from the Feynman diagrams, and they, represent unnormalized densities that we need to integrate to get the total cross-section. And so you can think about improved sampling procedures. So this is very, very similar to what Julian was talking about. So actually, we also use, quadratic spline flows and normalizing flows to, generate, approximations of the true matrix element in a normalized way. You can also think about, okay, can you somehow, compress like an entire sample of simulated data into a neural network so that instead of shipping individual events around, you can ship kind of a neural network as a data product. And so this is, I think, where the connection to Lattice is closest, right? And so Julian just gave a very nice talk on flows, as a proposal distribution for field configuration sampling. And there also work on kind of preconditioning, the Dirac equation. And so generally, I think what is shared here between particle physics and Lattice is that machine learning is very, very good at finding approximate solutions, right? And so it will never give you like an exact answer. And so the challenge in having machine learning systems kind of at the level where you need to exact results is that you need to be able to formulate the problems where like a approximate solution is already useful, right? And so having like a good proposal distribution for importance sampling is useful. It doesn't need to be perfect, but it kind of helps speed up the things. And also having like a slightly suboptimal preconditioner is also not a problem. You're still solving the problem exactly, but you're trying to find like a good initialization, right? And so this is, I think, like a good strategy to integrate machine learning where you need to have kind of reliable or provably correct results, right? And reconstruction is the same thing. It's fine if we don't find the perfect reconstruction algorithm in particle physics. Our measurements will still be correct, right? But we might not have the best precision, and that's the cost that we are paying. Okay, so then, you can go down the simulation pipeline. There's a lot of work on, machine learning for QCD, so for jet generation or hadronization models. And also a very big aspect is kind of detector simulation, which is by far the most costly thing. And so the simulating the interaction of particles with detector material is, something where there's a lot of interest in trying to replace this with generative models. And so the Atlas experiment where I work is actually the only LHC experiment where this has been actually deployed into production, right? So there's a lot of work on kind of toy models, but actually having this in the production pipeline is something that took a lot of work. Okay, so then we can maybe switch to beyond standard workflows. So instead of training a machine learning system that only kind of takes some input, you can imagine that, okay, depending on what physics I'm looking at, I want to reconstruct or look at the data differently, right? So if I'm looking for supersymmetry or I'm looking for Higgs decay, I need to have different observables, right? And so typically what we do now is that, okay, we train like one machine learning system that looks at the data and kind of compresses the data into like a representation, but it doesn't get a lot of information of which what theory we're looking at. And so there's a lot of work on what's called simulation-based inference to basically also inject into the machine learning system what specific question are you trying to ask, and the machine learning system will try to find an optimal representation of the data for this exact problem. And then if you change your question, it will also change the angle at which you're looking at the data. Okay. And then, you can also have machine learning outside of this entire data, reconstruction pipeline. And so, for example, you can imagine the theory space is very, very big. There are lots of supersymmetry models, and so it's not obvious which ones should we be looking at. And, can you maybe use machine learning as a type of assistant to suggest which parts of the theory space to explore? And so, we want to explore theories where we are sensitive and that there are theories that are not trivially excluded. And so this actually works, and we have done this in Atlas, where the machine learning system suggests in the 5-dimensional kind of beyond, like, dark sector search, which theories exactly should we be looking at to, ideally use computational resources to find where this exclusion boundary is. Okay, so this is also fairly speculative still, but a very exciting field. So at some point, maybe also for Lattice interesting, sometimes we're going to build new detectors, and so the EIC is a very good example. And so the question is, okay, what is like the optimal detector design? And so in industry, there's a lot of work on kind of optimizing hardware, and there's interest whether or not you can use machine learning in this. And actually, it turns out you can do it. And so for EIC, there's some work happening also from IFI on doing kind of Bayesian optimizations, so not deep learning, for optimizing the details of the detector design, what the angles of the different modules should be. Or at the SHIP experiment that was planned at CERN, there was kind of optimizing the layout of the magnetic field, and you can try to basically use gradient descent to optimize the space of possible detector designs. And so this is an example of what this looked like. And so you can try to differentiate through like a stochastic process, like a particle shower, to optimize the material distribution of your detector to find like a specific goal. So for example, if you want to have the showers at a very compact compact radius, you might want to optimize the material distribution for this, and you can still do gradient estimation even for complicated things like particle showers in a detector. Okay, so then I'll kind of get to a close. How am I with times? Okay. Great. So then, so there's all the stuff that I talked about is kind of how you actually use kind of machine learning models inside of the process. And so I think, especially in the last year, there was a lot of work on, or excitement about, things like ChatGPT and so on. And it might be that, okay, a machine learning system might not only have like an impact on like the actual thing that we run, but also how we develop software. And so a lot of big part of particle physics is developing software. And this code, this is something I generated, and this is kind of like a typical Atlas code, and this came directly from ChatGPT, and this kind of just helps kind of with programming, and I think this is clear to have like a big impact. And yeah, so I'll end with this. Maybe just kind of interestingly, I started out with, we are kind of 10 years into the deep learning revolution. And so if you look at another transformative technology, so 10 years after the invention of the World Wide Web was 1999. So if maybe the people that were around back then. Remember what the internet looked like in 1999? It looked very different than today. And so this is where we are. We are kind of in the 1999 of deep learning. And now 25 years later, there's a lot of transformation. And so I think if we look back in 25 years, things like ChatGPT will look very, very primitive. And so there's a lot of dynamism and a lot of very steep trajectory. And so it's going to be very interesting where we are going to be in 25 years. Okay, so I'll close with these nice quotes that I think capture the spirit of what is happening in machine learning and particle physics well. And thanks for your attention.